Intriguing title, so I'm eager to see this. So take your time.
Okay, good morning everybody, and thank you very much to the organizers for organizing this very nice workshop and for inviting me to speak. And it's a real pleasure to be back less than 1 year since my last visit. Today I will tell you about a way to look for dark matter colliders, a way which is slightly different from the one we heard in the first talk, because the type of candidates I will focus on will be different candidates leading to different signals. And I will show you how we could speculate about the early universe, in particular the universe before BBN, if we manage to see something a collider, which is a displaced event. So before I get to the main part of my talk, I would like to put this work on a broader perspective. And I would like to remind you something that I'm sure is obvious to most of you, but just to give you all the caveats to my analysis. I would like to remind you that there are bounds and bounds. So what do I mean by that? The different bounds, for now we only have bounds. Different bounds, they have different implications at this moment. And hopefully very soon, once we start to get signals, the different signals will deliver different information. So by different, I mean with different search strategies. So I would like to give you some examples. For example, you can search for dark matter through the so-called astrophysical searches, such as direct detection, indirect detection. So the good thing about these searches is that you are actually looking for dark matter. Namely, you're looking for something which is stable on the universe time scale. It's abundant in our galaxy. But you have to fight with several uncertainties, such as the velocity distribution, the local density, the density profile in the center of the galaxy, and so on. Then you can look for astrophysical production of what it could be the dark matter, such as stellar cooling mechanism. In this case, you are not sensitive to the uncertainty of the velocity distribution or the density distribution of the dark matter, but on the other hand, you have to rely on the modeling of quite complicated systems, for example, the explosion of a supernova. And also, these may not be the dark matter. It may be subdominant. It may not be stable on cosmological timescales. Okay? Then finally, there are cosmological bounds. Within a given model, you can compute the relic density. Okay? And there are cases such as the WIM miracle or the ones I will discuss today, where this calculation is very solid, is very reliable. But as we heard yesterday in the talk on non-thermal dark matter, you need to specify cosmological history. So there is this big caveat that could alter your conclusions. And finally, I get to the accelerator base in general. I will focus mostly on particle colliders. Here, it's a very controlled environment. It's a collider, so we know what we're doing. We don't have any source of astrophysical distributions or velocities. But again, the same caveat holds. It may not be the dark matter. It may not be stable. It may be a subdominant component. It's just something invisible. So with these caveats in mind and with this overview of the different searches, that's what I will talk about today. I will talk about the interplay between these two types of bounds for now. And the reason why I focus on these two is because the candidates I will focus on are too weakly coupled to give any signals in the first two. Okay, so I remove the first in the top because they are not expected to be relevant for the candidates I will discuss. And in particular, I'm interested in the interplay, and more specifically, I would like to know if by observing something here, in particular a displaced event, can we learn something about the early universe? So that's my goal. I want to focus on searches at colliders, and I would like to see if I can learn something about the early universe. That's my goal. Okay, so here are the main players of this talk. They're called FIMPs. It stands for Feebly Interacting Massive Particles, which will be also the subject of the next talk. And in this cartoon, I have the generical theoretical framework. Okay, so there is the standard model. These are all the particles we know. And then there are BSM degrees of freedom. I divide these BSM degrees of freedom into particles which I call bath particles, because they are in thermal equilibrium at very early times with us, with the standard model particles. So they have a strong connection, strong enough that they thermalize, okay? I don't mean SU3 QCD. I mean strong enough. And then there is the so-called FIMP, this X particle, which is very weakly coupled to both. In particular, it will never thermalize in the early universe. So I just put one of these films just for concreteness. There could be more than one. It's just for simplify our discussion. And then I'm going to impose a Z2 symmetry according to which these particles are odd, just because I want, in the end, the particle to be stable. And I'm also assuming that X is the lightest Z2 odd particle. So this is the dark matter candidate. Of course, you can imagine different situations where X is actually heavier than some of the bath particles. It still plays a very relevant role. So it doesn't have to be the lightest in cosmology, because you can produce this X and then they will decay. So this is just an assumption. I want my dark matter particle to be a film. Yeah, so in exactly. So you can imagine about, you don't know, the MSSM and the gravitino. Okay, that's one example. And the gravitino is the LSP. But I will be very general until some point where I specify some explicit construction. But this could have gauge interactions. They can have renormalizable interactions with us. So I'm just assuming they thermalize.
Yeah. When you quote these people, then it's just a cultural question. So films were there forever, right?
Yes.
But if people call them film and then we need to quote them.
So I think the history is that they realized. Yeah, so I think I would like to give some credit to these people because they realize that if this coupling, the coupling of X with the visible sector and the extra sector is renormalizable, then the production is infrared dominated in the sense that it doesn't depend on the reheat, unlike the gravitino case. So they call films a framework where the density is calculable only in terms of parameters you can measure in a lab and not cosmological parameter. So that's the history, but in my case, actually, it will not be the case. So yes, I know there were examples of films in this case before, but
Francesco, the X interacting with the other dark sector is also must be very weak in this case.
Yes. So I'm sorry, I didn't write it again, but I used the same code for the line. Yes. So it's exactly. So X will never thermalize. Very good. So this doesn't look very promising. Okay, because all we have left today is this X, very weakly coupled. In particular, if you put numbers, you see that you will not see anything at direct detection, you will not see anything in indirect detection, you will not see anything in monojet, as we heard this morning. So this is a nightmare for dark matter searches, although there are exceptions. For example, if you have a very light mediator in direct detection, you can have some enhanced rate, but the general message is that films are very difficult to detect. Okay, so today and also in the next talk, we will tell you about a way to see these films at colliders today. But before I do that, I would like to remind you how this particle gets produced in the early universe. In such a way, we get a feeling of what kind of couplings we need in order to have a successful production. And then we will see the experiment. So let's first see how films get produced in the early universe. So the message is very simple here. You have this bath of particles, all in thermal equilibrium. They occasionally talk to each other. They may decay. They may scatter. And in these events, you can have X produced in the final state. So what happens after X is produced? X is produced, and it free streams until today. No thermal equilibrium, no back reaction. The reaction goes only in one direction. So that's how freezing works. So with the cartoon, if this is the primordial bath of particles and this is a comoving volume, imagine the universe after inflation. The universe is reheated only with bath particles, not with films. This is an assumption. We heard yesterday that the inflaton can have a branching ratio to these dark matter candidates. I'm assuming that the amount of films produced at reheating is something small. So the universe at very early times looks like this. Yes. Yes, of course. This is an assumption. This is an assumption. But it could be a subdominant contribution to the amount. Yes. So unless you specify a model, this is just an assumption. And if you have a model, of course, the case you mentioned, you have a branching ratio that you can compute. But it could be a subdominant source of production. Exactly. And then the main source of gravitino could be from scattering. Okay, so at some point, which I call freeze-in epoch, and I will be quantitative about when this happens, but this is very important. When is very important. Then you have these reactions becoming effective and dumping X in the early universe. So you produce this X, and they freeze stream until today, and that's how you make the dark matter. So this is a qualitative picture. So in order to be quantitative, we have to specify a process. Okay? So let's say that a Bath particle decays to a standard model particle plus X. So I do freeze stream from decays. So I can estimate quite simply when this production is maximally efficient just by estimating the amount of co-moving X, so Nx over S, S is the entropy density, at the given temperature.
So you consider that X is produced only by decay?
Only by decays.
It can be produced by collisions.
Yeah, so I will come to collisions later. For now, let's say decay is the main source, but collisions will play a role. So for now, let's say decays. So this is a very naive estimate. There is the lifetime of B corrected by the Lorentz dilatation factor because these particles are moving, so they have kinetic energy. And then this is the age of the universe. So you plug the numbers, assuming a standard cosmological history, and you see that this process is infrared dominated. The lower the temperature, the more efficient this process is, which is good because it means that we don't have to know about the details of the very early universe. We are just focusing on the time when this is mostly efficient, and of course this naive estimate breaks down when the temperature becomes equal to the B mass, because then Maxwell-Boltzmann suppression kicks in, and B particles will start disappearing. So let's be even more quantitative. The way you compute the Rayleigh density is through solving a simple Boltzmann equation, which you can recast for the co-moving density. The solution is just a numerical integral, and here are some plots. Co-moving density on the vertical axis as a function of time. Here, I call this time is just the inverse temperature, but of course, if the temperature goes down, the time goes up. So the arrow of times is from left to right here. And you see, this is the infrared domination I was talking about. Most of the X, I say gravitino, most of the X are produced around the time when the temperature is around the B mass. Okay? That's why I can be sloppy about the early universe physics and integrate this equation from X equals 0. X equals 0 means infinite temperature, because the contribution from very early times is something negligible. So this will be important, but this is the infrared domination. Another important comment about this equation is that there is a dependence on the Hubble parameter, h, and this Hubble parameter enters because, of course, you solve the Boltzmann equation in the Friedman-Robertson-Walker background, and the cosmological history will play a role as well. So now that we know how to compute the Rayleigh density, let's come to the collider signal I was talking about. So B particles, imagine they have...
Just to contrast with, say, a gravitino case, it's going to go as a positive power temperature?
Yes, so if you produce gravitino from decays, actually, this is still true. But then you also have scattering, as Carlos was mentioning, and that typically is the leading contribution. It doesn't always have to be the case, but I will come to scattering later. The key difference is that gravitino interactions are not normalizable, and I have a slide about that, so I will comment. Good. Okay, so collider signal. Imagine these B particles have gauge interactions, or they are coupled to us. We can produce them at colliders. Typically, will be pair produced. And then we can observe the decays of B at colliders. Well, that depends. It depends if this decay is fast enough that we see on the sides of the detector, because if the lifetime of this B particle is too long, then for all purposes, these are stable particles. So the nightmare comes back here because we thought we could test this. And then you see that this is a very simple phenomenological parameterization in terms of three parameters: mass of B, mass of X, decay length. So if I fix the Rayleigh density, I can compute the decay length as a function of Mx and Mb. And you see that, unfortunately, Mb cannot be too different than the hundreds of GeV, because it's something we want to produce at collider, so we cannot span over orders of magnitude. For the mass of X, we could, but in order to bring this decay length really down, we have to lower Mx below the MEV. Okay, so it's possible that you get a displaced event if you get lucky, if this Mx is very, very small. And it cannot be smaller than few keV because of Lyman alpha bounds of warm dark matter. But I would say displaced vertices are not a generic prediction of this framework. So this seems to be the end of the story.
Again, remind me why MB cannot be arbitrarily large.
Oh, because you want to produce a collider. So if you put 1 million of TeV, then you will not see that. Otherwise, the mechanism will work in the early universe. It's only because I want to see that collider.
This lifetime for the particle is derived from which consideration? This formula.
Rayleigh density. From
Rayleigh density.
this equation here.
Okay, I see.
I want to impose that m times y is the comoving dark matter density we observe today.
That's only for decay that.
Only for this decay, yes.
This decay that.
Yes, yes. But that's the best scenario you can test a collider because you first produce B and then you decays.
But you can, well, be not in thermal equilibrium and slowly increase number of dark matter particles, not through decay, but through the kind of.
You mean scattering?
Yeah, but
Scattering, yes, but then you have a more complicated topology, and it's not obvious you can test this at collider. Imagine you need scattering of 2B particles. Then you have to produce more particles at collider, yeah.
So why this does not depend on lambda B, the coupling?
So lambda B is hidden here in the tau B, yes. So this system is a system of 3 independent variables, the mass of X, the mass of B, and the coupling. So these are the 3 independent variables. I impose Rayleigh density, and I get a relation among the 3. So I traded lambda B for tau B. So it's hidden here. Very good.
What's the size of the coupling? If you take this,
So you can see from this equation here, it's typical size are 10 to the minus 8 to 10 to the minus 12 if you want to impose the Rayleigh density. So I would say for this mass, large mass is more like 10 to the minus 12. It's very small. Well, it could be long-lived, but this is really long-lived, like 10 to the 8 centimeters. So it's, well, you can, well, okay. You will detect something which is a heavy, stable, charged particles. That's new, we will be happy anyway, but the connection with dark matter will not be obvious. Because you don't know if this particle decays to what, and so you cannot connect the decay length to the Rayleigh density. But yeah, that would be a signal, but it will be hard to connect with dark matter. Production, yes, well, I'm going to consider in the future particles B which are gauge multiplets. They are charged under the gauge of standard model. So once you specify the spin and the quantum numbers of B, the cross-section is something you can compute. So I will be more specific about what B is later. OK, so is this the end of the story? So let's try to be optimistic, OK? And instead of saying that this is a scenario we cannot test at colliders, let's think the other way around. Let's imagine you see something at collider. Okay, you see a displaced event at collider where you have something, a charge track, decaying to some standard model particles plus missing energy, which is what you expect from this type of models. Now, in the quite optimistic scenario, you can measure the mass of B and also the decay length. Okay? So it will be difficult to measure the mass of X unless the mass of X is very close to MB. Let's be not too optimistic. Let's say that we measure MB and tau B at collider. Well, at that point, we have an event. We have numbers. We can plug numbers. Then we learn that for sure the missing energy, assuming it's cosmologically stable, of course, this is the caveat I mentioned in the first slide. Then we get the bound on the mass of X. The mass of X cannot be too large once MB and tau are fixed, because otherwise I overproduce the dark matter. Or reminding myself that this number came from a calculation assuming a standard cosmological history, I can try to see the interplay with what happens once I change cosmological histories. Okay, so this is the main message. Displaced event at collider, once we observe them, they give us information about the combination of the dark matter mass and the cosmological history of our universe before BBN, because the mass of this B, when this decay happens, is hundreds of GeVs. It's way before BBN. Okay? So
X cannot be MEV?
it can be MEV.
So
It's, well, I would not call fine-tune. I would just say that it's a corner of the parameter space. It is not a generic prediction. But I will tell you the opposite in the next slide, because this equation depends on a standard cosmological history calculation. And I will give you two examples where actually this is not the case.
It also assumes that the whole dark matter is X.
Yes, so there is this assumption, which of course cannot be checked at colliders because of the caveats I mentioned. So I was honest in the first slide.
If it's not, what direction does it go? If X is not the whole dark matter?
Well, good. No, okay. This is something I would like to emphasize. It may not be the whole amount of dark matter. It cannot be more than one we observe. So you get an upper bound on the mass of X, just from a collider measurement. And in general, if you play with cosmology, you get upper bound on dark matter bus combined with the cosmological history. Okay, so before I describe models in details, let me give you one example, actually a couple of examples where if you modify the cosmological history and you do in a way which is not completely random, but you do that in some sort of motivated frameworks, displaced events are a generic expectation of this class of models. The first case I have in mind, and this is something I did in collaboration with people when I was in Berkeley, we studied the freezing happening during inflationary reheating. So this is a time when the inflaton starts oscillating around its minimum and is decaying to standard model particles, reheating the standard model and creating the standard model bath. So I'm interested in dark matter freezing through this epoch. And this epoch is not an instantaneous event in the most general framework. There is a maximum temperature, as we saw yesterday in the talk on non-thermal dark matter. There is a maximum temperature, and then the radiation starts to redshift with a different exponent compared to the standard case. So, of course, I want this maximum temperature to be above the B mass because I want the decay to happen. And then there is the usual reheating temperature, which is below the B mass. And so if freezing happens in this epoch, the radical density calculation has to be revised. So that's what we studied, and this is a plot where here you have T reheat, here you have the decay length. We fix the B mass, we consider a wide range of X mass, and you see that unlike the standard chronological history, in this case, displaced events are a generic prediction.
What are the bands? Could you explain?
Oh, the bands are just so this is 10 to the minus 2 centimeters to 1 meter. And so these are bands to check where you expect to see in the detector. So just if you see in the tracker or in the other layers of the detector. The other case we studied, this is something I did with my collaborators in Santa Cruz. It's not important at all. GB2 means a wild fermion. If GB is equal to 4, this is a log scale. So it's a number of, oh, sorry, it's not the coupling. It's not the coupling. It's the number of degrees of freedom of V. So it's a wild fermion. No. Otherwise, it's. Otherwise, it's.
But if you change the number of degrees of freedom, the plot doesn't change a lot.
Well, it will change because let me show you. In this equation, the amount of X you produce depends on GB. Because if you have a big multiplet, once you're in equilibrium, you have a degeneracy factor. Then you have But these are small numerical factors. This is a log plot. You could barely see by eye the difference. This is just, we had to choose something for concreteness. Second case, kination. So this is also a motivated modification of the cosmological history. It happens in theories where you have quintessence fields addressing the cosmological constant today, but they go through a phase where you have the opposite behavior in the equation of state. In the early universe, the kinetic energy dominates over the potential energy. Today, you have that the kinetic energy is small, and so W equal -1 to have the cosmological constant. But this is what you achieve today. In the early universe, in some models, you get that this kinetic energy dominates, so W is 1, and then you have a different redshift behavior, and so we also studied freezing in this epoch. And again, here, for different M chi, for different MB1, we found that again, using the same bands I identified before, 10 to the minus 2 centimeter, 1 meter, and then 100 meters, displaced events are generic also of these modified cosmological histories.
Why is not IR dominated, or why do you care?
What do you mean is not IR dominated?
I mean, why
Oh, here? Oh, it's it's simple. So this is the temperature where radiation kicks in, okay? Imagine this temperature to be very low, but above BBN, of course. And the B mass is more or less like here. So it cannot happen here just because the Barth particle disappear because of Maxwell-Boltzmann suppression. So that's the reason. So this is not quite the rate. In the case of kination, the energy density redshifts as a to the minus 6. So you don't need this field to decay. You don't want it to decay because you want to still provide the vacuum energy today. So the way radiation kicks in is just because it redshifts slower than this field. It's a to the minus 4 versus a to the minus 6. So we call this AR. It's not really reheating. It's the crossing of the two lines. Okay, so again, also in this case, so this is just to give you two examples where you have motivated modification of the cosmological history where displaced events are actually expected, and they're typical, they're not just there in the corner of the parameter space, okay? Now, before I go and discuss, oh, this one? Or because MB1 is just kinematics. It cannot decay to chi. It's exactly. So you want chi to be the lightest. Okay, now we come finally to the question about scattering. So I would like eventually to discuss explicit models. I don't want to. So far I gave you a very phenomenological parameterization in terms of mass of X and mass of B, tau. Eventually I want to write down Lagrangians and do calculations and see what happens. Before I do that, there is something that I need to tell you, and it goes back to several questions I got already about scattering. So this decay is likely to be mediated by some operator, okay? Now, the question is this operator normalizable or not? This is very important for the scattering contribution. Why? Because scattering contribution is actually unavoidable, because you have this vertex here, you just attach two standard model particles, and then it has to happen, okay? Now, you can do a naive calculation, okay, naive estimate, as I did before, trying to estimate when freeze-in is mostly efficient, as a function of the temperature. And this is what you find. D is the dimension of this operator here, okay? This is just quite simple. You just do a dimensional analysis, basically, okay? So if D is equal to 4, 2 times 4, 8, minus 9, minus 1, you get a negative exponent, so you get infrared domination. And we are safe, and we don't need to worry about what happened at very high temperatures. So all the discussion we had still holds. What about if it's not normalizable? We already know one case, the Gravitino, which is very famous, very motivated, and very not renormalizable. Not very. It's dimension 5. So, but it's enough. It's 2 times 5, 10, minus 9, 1. So you see that the higher the temperature, the more efficient the production is. This is a problem because now we need some UV cutoff when we integrate the Boltzmann equation. This cutoff could come from, for example, the reheating after inflation, as it's famously known in the case of the Gravitino. Okay, so before I discuss models, we need to keep in mind this important difference. Well, at some point you achieve, yes. Yeah, at some point you say the temperature will be as high as the cutoff, right? Yes, but I mean, imagine the Gravitino with M-Planck suppressed operators, then you have inflation at a lower scale, more likely, so the cutoff will be provided by inflation. But you're right, and in the case of a generic normalizable operator, it depends on the scale. Very good. Okay, now let's finally see some explicit construction. So let me start from a top-down case we studied. This is also something I did with collaborators in Berkeley. And this is a motivated example because these are theories that address two of the major problems in particle physics, the hierarchy problem and the strong CP problem. So you have the hierarchy problem solved by supersymmetry, strong CP problem solved by the Paycheck-Wheat mechanism. And in these theories, you have two films, not even one. You have two, because the Gravitino and the Axino are both very weakly coupled. the gravitino has M-Planck suppressed interactions, and the axino has interactions suppressed by the scale of Pei-Chai-Queen, which is very high. So it's quite likely that they will never be able to thermalize in the early universe. The gravitino has only non-renormalizable coupling, as we said already many times. What about the axino? It depends, because of course you have the supersymmetric generalization of the GG dual coupling. That's a dimension 5 operator suppressed by the Pei-Chai-Queen scale. But there are theories, the so-called DFS-Z theories, where the combination H up, H down is charged under Pei-Chai-Queen, that they have this operator in the superpotential, and this A is the action superfield. So once A gets a VEV of the size of the Pei-Chai-Queen VEV, which is VPQ, then you get the mu term in the MSSM, which would be forbidden by Pei-Chai-Queen symmetry. Okay, so you also have a normalizable interaction, which could be relevant in the infrared, because these electroweak kinos could decay, and then of course also the wind on the, if you have mixing, let's say, yes, electroweak kino in general, both charged and neutral, they can decay to axinos, and this would be a contribution which is infrared dominated, and it could be dangerous. Okay, so that's what we studied, and we got interested in this problem. Besides the top-down motivation of the theories, we got interested because if you do an estimate of their, so assume axino LSP, and then compute the amount of axino produced by freezing, by this type of freezing. You can compute without any sensitivity on Thierry heat. Compute the abundance of axino freezing, and this is the abundance you get divided by the amount we observe. Okay, so this number, we would like to be 1. It can definitely be, it cannot be definitely more than 1. Okay, and this is how it depends. I put for the axino mass a weak scale mass, mu also, and Pei-Chai-Queen scale 10 to the 10 GeV. These are the typical numbers. So you can play with numbers, but again, you see that unless you confine yourself to very large F and very small a, MA, then you badly overproduce the amount of dark matter. And this is a problem also if the axino is not the LSP, because this axino will be produced and they will eventually decay to whatever is the LSP. So it is a problem. This theory have a problem. So I will make a long story short, because in the interest of time, in the interest of telling you what I'm doing right now. So I will just summarize what we did. And in these theories, there is the problem, which is the axino overproduction, but there is also the solution. The solution is the so-called suction. Is the CP even partner of the axion, the CP even partner of the axion. And its mass is not protected by Pei-Chai-Queen, it's only protected by supersymmetry, so the suction mass is of the order of the weak scale. It's model dependent, but that's the size we expect. And this suction has a early universe dynamics very similar to the one of the axion. It's frozen by Hubble friction, and then eventually starts oscillating around its minimum. And the difference with the axion is that the mass is much larger, so it will start oscillating much, much earlier with respect to the axion. And what happens is that these oscillations behave as non-relativistic matter, so they eventually take over the radiation, and you have a phase of early matter domination. So this is a nice example because we have everything. We have a complete theory where you have supersymmetry, you have the axion supermultiplet, and you also have a complete description of what modifies the thermal history, the suction. So we did a self-consistent calculation. We studied dark matter, in particular axino and gravitino dark matter in this scenario. And then, since I only have 5 minutes left, let me just tell you the main message. Imposing the dark matter relic density naturally points toward displaced signals at collider. Okay? So unlike the estimate I made at the beginning, here I have a framework where I can completely control the modification of the thermal history with the suction, and displaced signals are typical in this top-down motivated construction.
What is the production mode?
The production mode, well, it depends.
What are you producing?
Oh, you mean the collider? Yeah. Electroweak kinos. It's mostly electroweak kinos. So you basically have this processes happening at collider, yes. Okay, so in the last 5 minutes, let me tell you what I've been doing in the last months, and this is work in progress with these people here in China and in Brussels. And so now I want to take a bottom-up approach. So instead of focusing on some motivated theory, in order to cover all possible cases, I would like to classify all the possible options I have for B and for Sm, okay, and for X as well. X is a singlet, so I only have to specify the spin. So basically, the classification is not too extensive because for Sm, we know what we can have. I'm assuming a two-body decay, okay? So these are the options. And once we specify the option for a standard model field, we also end up specifying the quantum numbers for B because X is a gauge singlet. So the only thing we have to specify are the spins of the dark matter and the spin of B. So this is what you get, a table with the different cases. We can discuss more about the table later. Let me just advertise related work. This was already studied in this reference from my collaborators in the singlet double model. So X is a singlet and B is mostly a doublet. There is some mixing. But they studied the standard cosmological history, so they had to confine themselves to very small mass for X in order to see displaced events. We are going beyond that. And also, well, we will hear more about this in the next talk, but in scalar dark matter coupled to standard model fermions, and in the case of instantaneous reading for cosmology, was also studied in this reference, and we will hear more right after my talk. So I will not say anything else. Okay, so let me just conclude with one example. And this is one example of the many we are studying, and so I will tell you what we do and what we would like to learn. So in my example, the dark matter is a fermion, chi. It couples to a lepton. It could be a singlet, it could be a doublet. We are studying both, okay? It's not very different. And then the B particle is a scalar which has the same quantum numbers as the lepton, just to preserve gauge invariance. In this specific model, you also have this portal operator, which we have to make sure is under control, but we check if this lambda is not much larger than 1, then there is no impact in the cosmology, because basically the dark matter production is controlled by this operator here, and this operator is just keeping B in thermal equilibrium, but B have gauge charges, so it's really a minor perturbation to the cosmology. It doesn't play. Yes. Yes. Yes, but even in the it's normalized. But once you put the soft mass, it's m square, m lepton square over f. Okay. Yes, exactly. So it's exactly what you see in this lepton gravitina. Okay, so a couple of plots before I conclude. So we are studying physics in the plane of the mass of the phi and the decay length of the phi, which is the same plot used by the LST collaborations. So here you see the current bounds of from the heavy stable charged particle searches, and then the one from displaced leptons, which is the signal you expect in this case. Now, in this plane, we have to specify the dark matter mass. So let's look at the case where the dark matter mass is 1. So you see that these relic density contour lines here, they are drawn for different value of the reheating temperature. So why I believe this is interesting? For now, we have bounds. Okay, so you already know you cannot live here. But imagine you see something in the future in this region here. Then you can start to say, okay, if the dark matter mass is 1 GeV, the reheated temperature cannot be lower than 10 GeV. Okay? And so on. So you get complementary information between the dark matter mass and the reheat temperature.
So they come from standard cosmology?
No, so this is from inflationary reheating with very low T reheat and reheating temperature below the B mass, and thermal bath produced above the B mass. Yes, so we are good. Okay, so we are doing this. Okay, if you do this by assuming cosmological history and you see something here, you are killed, okay? So you can start to consider different cosmology. We are considering the first case I pointed out before. Reheating after inflation with large Tmax, so you populate the thermal bath with B, and these are the results. Now, how, sorry?
How multi-value, I mean, you change.
Yeah, so I think it's fair to say there is a degeneracy between the dark matter mass and the reheat temperature. For example, here you have another plot where You put the dark matter mass to, we say 12 keV. This is a number coming from warm dark matter bounds. And you see that the real temperature you get is lower. So you may, it's true. There is a generosity, unless you are lucky enough that you measure the mass of chi at collider, for example, from some distribution of the missing energy, but that's tough, and chi cannot be too light. But if you don't measure the mass of chi, you get an information in this two-dimensional parameter space, but you could imagine, for example, measuring Thierry heat from the imprint on the primordial gravitational wave spectrum. Okay, now we also have that handle to probe the early universe. So there is a degeneracy.
You know how we can measure the mass of the chi? Potential. How we can measure the mass of
the mass of the chi is by studying. So what you see at collider eventually, you see this track of B, and then you see in this case, the lepton coming up. So you need to have a chi close enough to B in such a way that you see the effect of chi in the phase space, and it doesn't behave as a massless particle on the. So there are studies, but chi has to be very close its mass to B, and it's not a typical situation. So I think it's difficult.
No, I thought so this is a charged particle.
The B, yeah, in this case it is, yes, because it's.
So if it is a long-lived charged particle, you should see it, right?
You see and then you see also a displaced missing energy.
No, I know, but I was wondering why the limits on extrapolate are so weak for C-tau 1000.
Oh, because you still see some decay, I guess. You see some, so we recasted the analysis. Yes. So.
But you fixed lambda, right? So, and then
lambda is the coupling here.
Yeah, and you say that if we see something, but how quick you change if we change the lambda? Or you say that we can measure lambda, or
well, if we measure the lifetime, lambda for you is the coupling.
Yeah.
Yeah. So the lifetime is as we saw before. Yeah.
This way we fix parameters of the model, and we really can test the technology application. I mean, if you say that if the mass of the phi, whatever measure will be there, then.
So I mean, this phenomenological model has three parameters: the mass of B, the mass of chi, and the lambda, if you want, the Yukawa coupling here. So in this plane, you identify a point which gives you two parameters, and then you still have a third missing, which is the dark matter mass, which is the most difficult to measure at collider. And I believe it's difficult. It's possible if you get lucky enough, but the dark matter mass is not something we expect to measure there. So. I'm assuming that's correct. So I believe that. No. That's fair. As I said, unless you specify a modification to the cosmological history, the model will be dead because of overproduction. So you need to, and you have to do. I think you have to do this study modification by modification, and then you need to hope to have some other way to test the early universe and get complementary information so you can pinpoint to a value of the dark matter mass. But yes, I have no more to say than that. If you don't specify the cosmological history, you cannot draw on this line. 1 minute? Very good. Conclusions. So, freezing particles are frozen in particles, frozen in candidates are very difficult to test because they're very weakly coupled. And one promising avenue is to explore displaced signals at collider. So today I show you that in some motivated modification of the cosmology, displaced events are actually expected. And then we studied one motivated example for the FIMP itself, which is the axino and the gravitino in this Sussi-Pechequin theory. And we did a careful study of all the parameter space, and we found that displaced signatures are actually what you expect because of the important role played by the suction. And more recently, we've been working, and this is work in progress, about the bottom-up classification of all the possible options for the decaying particle and the standard model particle in the final state in order to cover all the possible options available and to exploit the full potential of the future LXC searches. Thank you.
So we have time for one question. So you?
So in the Axino example, can you, I mean, you had typically overproduction of Axinos.
What? Axino, okay.
Yeah, in the Axino case, you have overproduction of Axinos, and then you had that use the Saxion to dilute this production, right? Because it dominates the early universe.
Exactly, yes.
But you can also, the Saxion can also decay to gauginos, right? To gluinos, for instance. How do you...
Well, so we studied all possible options. Of course, this statement is true if the Saxion mass is below twice the gluino mass, if it's kinematically allowed. So you know the gluino bounds are quite stringent now, so you need a Saxion of UTV. So the Saxion we consider in this case was more like hundreds of GeV.
Just a very quick question. Have you taken into account in this work that the supersymmetry is broken by temperature? I mean, you have some soft scalar curves in the potentials, for example.
Yes.
So in the case of Saxinos, have you introduced some corrections of the scale of Hubble for?
So that I believe is a small effect to the mass of the superparticles.
Yes, it affects them.
So it's I don't think it's affecting the conclusions.
Mm-hmm. Okay.
So let's thank the speaker again.
Could you give it to me? Yeah. Okay. And this is on. I leave it on. Okay? This is for the video.